Hey, welcome back. So this is Calc 2, 1620. We are continuing on with this reinterpretation of our Riemann sum as an accumulation of volumes of objects, and we kind of use that to determine the overall volume of particular objects. Last time we saw the disk and the washer method. This time we'll see the shell method. So what are shells, basically? So shells, and we'll begin with x-axis rotations. Shells are basically just cylinders with holes in them. Like if you ever saw the Flintstones, the wheels on their cars were, I believe, shells. So let's take a look at the development of the integral in this context. So let's say we have some sort of region that we want rotated about the x-axis. So we'll say this region. In this case, with shells, the rectangles that we're using are parallel to the axis of rotation. So in this case, the rectangle is kind of given by a y value, its location, y sub I, and then the base of the rectangle is change in y. And our Riemann man this time is running up the flagpole in this direction. Okay, so the object that's getting rotated out, like I said, is kind of like the wheel of a Flintstones car. It'll end up looking like this. And here are our axes from before. So I guess it's in 3 dimensions, so you put in another axes there. Right, so the original rectangle, where did it go? It's sitting right here. And the Riemann man will add up a bunch of these, and essentially what you're looking at is kind of a, well, at least in this case, what you end up with is kind of like a wedding cake type picture. There'll be a bunch of shells inside of other shells, and yeah, it's like a wedding cake in this case. So anyways, the Riemann man's job is to add up the volumes of these shells, and so we need a volume formula for this thing, right? So how are we going to do that this time? The trick or the idea I saw in the Stewart book, this isn't in the Larson's book, but what you're going to do is kind of take this shell and cut it, okay, along this blue dashed line, and then lay it out. Okay? So basically unravel the shell and then find the volume of that object, because this object's a little easier to find the volume of. It's just length times width times height, right? Yeah. Okay, the red rectangle in this picture then is, going to be somewhere in here. The cut is kind of on the edge there, but we'll use that rectangle to kind of finagle a formula for the shell, for the volume of the shell. So okay, let's go at it. First off, the radius, I guess, would be the distance from the x-axis to where that red rectangle is. This would be like the radius of this shell. So I need that dimension regardless. And where is that dimension on this unraveled picture? It's basically well, I guess I'm going to need it eventually. I guess I'm getting ahead of myself here. One thing at a time, I guess. Well, what do I need? So on this picture, on this picture you need this dimension. So basically the height of that rectangle. So looking at the picture, I don't even have it labeled. Maybe that's the issue. You're going to have some function. It has to be in terms of y. So the height at position y sub I of that rectangle is given by g of y. So this distance would be g of y sub I for that particular rectangle. This dimension here is going to just be the change in y, right? So it's just change in y. And then the dimension I need the radius for would be this dimension. And this takes a little bit of creativity, creative thinking. What is that length? Well, that length is the length around this wheel thing, the shell thing, right? So let me put it, looking for a good color here. It's this distance, basically, that I'm looking for. And we can get that by formulas from geometry for circumference, right? So we'll say that distance is 2 pi r, 2 pi. The radius in this case, where I kind of already let the cat out of the bag, this distance is the radius from the x-axis to the location of the rectangle. That's just the distance y sub I. So this would be 2 pi r, or 2 pi y sub I. And then if you just multiply those three together, you get the volume of that particular shell, right? So the volume of this thing is going to be 2 pi y sub I, g of y sub I, times change in y. Okay. When we start looking at more general versions, like rotating about non-axes, the y sub I will change. This radius part can be variable. So instead of just always putting y sub I, it's going to be some function of y sub I in the book. So in general, they'll call this rho of y. So your volume formula in general will be 2 pi rho, which looks like a p, of y sub I times g of y sub I, which you're going to call in general just a height function, h of y sub I, and then times the change in y. So as the Riemann man runs across, we take the limit as the number of these shells goes to infinity, and our ending integral, sort of du jour, is the integral of 2 pi from c to the d of p, or rho of y, h of y, dy. Okay. So for the disk method, you're always identifying radii, that r of x or r of y function. Now the things you want to identify are going to be the radius function and this height function. Okay. Okay. So let's take a look at an example here. We want to deal with the region characterized by y equals x cubed, y equals 0, and x equals 2, and we want to revolve it about the x-axis. Okay, so first get a picture. 2, we're going to 2, and then y equals 0 is just the x-axis. At 0, y equals x cubed is 0. At 2, y equals, when you put in 2 for x cubed, you get 8. So it's up to here. You kind of know what the cubic looks like, hopefully. Looks like this. So the region we're worried about is this region, and we want to rotate it about the x-axis. So again, with shells, the rectangles are parallel. Okay, so here's my little rectangle located at position y sub I, and I need to get a formula for the radius, and then a formula for the height. So when you're going about the x-axis, the radius is always going to be just y. Okay, it's basically the distance from the x-axis to the rectangle. It's this distance. Okay. Then the height is, in this case, it's a difference between two things, right? So that red rectangle is formed by taking the difference between this rectangle, which is a constant, it's 2. Right, so the first rectangle is 2, minus, in the red rectangle's case, this distance. Okay, so that distance is given by the y equals x cubed formula, but we need it in terms of y. Okay. Basically, you could tell you need it in terms of y because the base of the rectangle is on the y-axis. Okay, so I'm going to have to go and work with this formula and get its inverse. So starting with y equals x cubed, you could take the cube root on both sides, or raise both sides to 1/3 power. And you end up with x equaling y to the 1/3. Okay. So it'll be 2 minus y to the 1/3 for the height of the red rectangle. And then of course, our Riemann man is in this orientation, running up the flagpole. Okay. And we'll have 2 pi going from 0, starting at 0 and going all the way to 8 on the y-axis, and then p of y times h of y dy. Okay, and then you just have an easy integral to do, so let's clean that out. Distribute. Integrate. And evaluate. So we get 64 minus 3/7. 8 to the 7/3. What the heck is that? Well, that's 8 to the 1/3 raised to the 7th power. 8 to the 1/3 is 2 raised to the 7th. 64, 128. Okay, so times 128. And then minus, plug 0 into the antiderivative. That's just 0. Going to need a common denominator of 7 apparently, so we'll have 2 pi times 64 times 7, 8 to carry the 2, 42, 43, 44, so 4/48 minus 3 times 128, 4 carry the 2, 6, 7, 8, 384. Over 7, and then subtract those two. 4 carry 4, 15, 64. So 2 pi times 64/7. Multiplying that out, you get 128/7 all over pi. Okay, so some arithmetic to do there. Right, let's move on to another one. Number 7, well, it used to be number 17. I'll just write it as an example. So we have y equals 1 over x, and we also have x is 1, and then x is 2, and then of course y is 0. That's the region, and we're rotating about the x-axis again. Okay, make sure I'm recording. Yeah. Okay, let's make this one the quiz du jour. So let me mark that in my notes. This is the video quiz. Un momento, por favor. Video quiz. Page 1, page 2, 7.3. Just 1 second. Okay, right, so first we want, again, a picture. Y equals 0 is just the x-axis, x equals 1, just right here. X equals 2, and let's put it right here. And then 1 over x, when x is 1, 1 over x is 1. And then when x is 2, 1 over x is 1/2. So we get this kind of picture. And we want to rotate this buddy around the x-axis. So the rectangles then, will look like this. And you may notice there's an issue, right? Okay, so in this kind of first region, below this green line, the rectangles are a constant length of 1. So, so there's kind of 2 regions we got to worry about. So in the first region, of course, the radius is no different than before. It's just y sub I, location of that rectangle. So the radius is no big deal. It's the height of these rectangles. So in this first region below the green line, the heights of the rectangles are constant. It's just 1. But then it changes. Then the heights of the rectangles become non-constant. So let me draw this blue rectangle here. Changes with the y sub i's. Okay? So it's variable. In other words, we need a formula for that rectangle, the blue rectangle. The radius formula is the same, it's just y, but this height formula changes. So what is the height formula then? Well, we need given y sub I, it looks like I'm going to have a difference of 2 rectangles, right? So that blue rectangle will be the difference between this rectangle here and this rectangle here. Okay, so that first rectangle is variable and it's dependent on this formula, y equals 1 over x. We need it in terms of y though, so we can multiply both sides by x and then divide both sides by y. Yeah, x is 1 over y. So the first rectangle is 1 over y, and then we're subtracting away the height of 1, and that should give us the formula to give us the height of the blue rectangles. Okay. Okay, again, the running man is going up the flagpole. Okay, so he's going in this direction. So on the y-axis, I'll be going from firstly 0 to 1/2. So you have to do 2 separate integrals for each area. So the first region, region 1, and then the second region 2 requires a different integral. Okay, so 2 pi, 1 times y is just y, dy, and then plus this other integral from 1/2 to 1 on the y-axis. So we have y times 1 over y minus 1 dy. Okay, and once you get it set up, I mean, that's 99% of the battle. The rest is just, do you know how to integrate? Okay, so we have 2 pi, integral of y is y squared over 2. And we need to evaluate this, and then plus 2 pi times, well, I guess I still need to kind of distribute here. So I have 1 minus y dy. We can kind of get the beginning out of the way. 2 pi times, plugging in 1/2, you'll have 1/2 squared over 2. 1/2 squared is 1/4. Divided by 2 is the same as multiplying by 1/2. 1/4 times 1/2 is 1/8. And then minus 0. So this will be just 1/8. Plus 2 pi. So this is kind of by itself and it's done. Plus 2 pi times the antiderivative of 1 minus y is y minus y squared over 2. And then I still have to evaluate that part. From 1/2 to 1. Okay. 2 pi over 8 is just going to be pi over 4, and then plus this other stuff. So 2 pi, I got to plug in 1 first, so 1 minus 1 squared is 1 all over 2, minus, plug in 1/2, 1/2 minus 1/2 squared, that's 1/8 again. Okay. Need a common denominator for the second part, so 4 over 8. Be pi over 4 plus 2 pi times 1 minus 1/2 is just 1/2. 4/8 minus 1/8 is 3/8. We're subtracting these. Another common denominator, so I'll turn them to 4/8. So pi over 4 plus 2 pi times apparently 1/8 should be pi over 4 plus 2 pi over 8, which is 1 pi over 4. So 2 pi over 4, which is pi over 2. Okay. Okay. Let's look at other axes of rotation now. So shell, and we're going to do the y-axis rotation. Now here everything will be terms of x, and the radius function will always be x. So just like above, maybe I should have noted that with regards to x-axis rotations. I really couldn't say because we didn't know yet, but the radius function p of x will just be x. Okay, y, right? So sorry. Edit that. So p of y is y. Okay. Let's go at it. So in this case, let's kind of derive it again. Here's the picture that we're dealing with. So now you'll have some function like this, and the rectangles are parallel to the axis of rotation. Because the base is on the x-axis, the Riemann man is collecting in this orientation. And if you were to rotate out that one rectangle, you would get sort of a sideways Flintstone tire scenario, where the red rectangle, maybe I should do that in red, is sitting right here. And again, we go ahead and cut it and then lay it out straight. So cutting it and laying it out straight will allow us to kind of think of it as a rectangular solid, and the formula is just length times width times height. So the height is the height of the rectangle, and that's given by whatever formula the curve has. So let's call it f of x. So this will be f of x. Then the width of the rectangle is given by change in x. Right? And then this distance is 2 pi r. And the radius in this case is just the distance to the red rectangle, which is given by x sub I. Okay. Then in general, v sub I will just be 2 pi times some radius function, of course in this case just x, times some height function in terms of x. And then if your Riemann man goes along and adds up all these sums, and then you take the limit of it, you get the integral of 2 pi from a to the b of p of x, h of x, dx. Okay, so let's take a look at some examples and see what we get. So number 11, we have y equals square root of x minus 2, y equals 0, x equals 4. And we want to, of course, do a y-axis rotation. Let's get a picture. Square root of x minus 2 is a shifted version of the square root function. It goes over 2. You can do some point plotting. At 2 it's 0. At 3 it'll be square root 1, which is 1. At 6 then it'll be square root 4. So 4, 5, 6 be square root 4, which is 2. Okay, so our square root x minus 2 looks like this. Y equals 0, of course, is just the x-axis, and then x equals 4, 3, 4, is this vertical line here. So the region we want rotated is this region, and we want to do it about the y-axis. The rectangles are parallel to the axis of rotation, so in this case it'll look like this. And that particular rectangle is located at position x sub I. So I need a radius function, and again, that will just be x. And then I need a height function for the heights of the rectangles, which in this case is given by the square root x minus 2. Okay, so no big deal. Plop it into your formula, 2 pi. The Riemann man is going in this orientation, collecting those volumes. And it looks like he's going to have to collect volumes from 2 to 4. He or she. I'll make your Riemann woman. Re-woman or something. Re-woman woman. Okay. So that is one of my favorite integrals in the universe. Most favorite integral in the universe. You have to do a u sub for x minus 2. Du is just dx. And then after you do that U sub, you realize the x's won't go away, so you need a formula for x. We'll just do that right there. Okay. So I'll end up with 2 pi times the integral, and I'm just going to drop the limits until the end, and then back sub x is u plus 2 times the square root of u times du. Dx is just du. I'm going to rewrite that square root of u as u to the 1/2. So this is u to the 1/2, and then I'm going to distribute. Okay. So this will end up being 2 pi times the integral of u to the 3/2 plus 2u to the 1/2 du. This will be 2 pi times u to the 5/2, just power roll, times 2/5, plus 2u to the 3/2 times 2/3. I'm going to remind myself to evaluate. So back subbing 2 pi times 2/5 to the times u, which is x minus 2 to the 5/2, plus 4/3 times x minus 2 to the 3/2. And now I can back substitute in my bounds, or my limits rather, from 2 to the 4. Okay. So this will be 2 pi times 2/5 times 4 minus 2, which is just 2 to the 2/5, plus 4/3 times 4 minus 2 to the 3/2, which would be 2 to the 3/2, minus that whole thing. If you plug in 2, you'll have 2 minus 2's in there, which will be zeros. So that whole second part will just end up being 0. Then we needed to do some simplification. I'm going to write it in terms of roots and pi. So 2 to the 2/5 is, what is that? It's 5/2, not 2/5, first off. Let's get rid of that. 5/2. Okay, so 2 to the 5/2 is the same as 2 to the 4/2 times 2 to the 1/2, which is 2 squared times root 2, which is 4 root 2. So we have 2 pi times 2/5 times 2 root 2 plus 4/3 times 2 to the 3/2 is the same as 2 to the 2/2 times 2 to the 1/2, which is 2 to the 1 times root 2. Okay, so this will be 2 root 2. And then we have 2 pi times 4 root 2 over 5 plus 4/3. Oops, did I write 2? It's 4 root 2 there. Sorry, guys. It's supposed to be 8 plus. It's pretty much the same thing, right? 8 root 2 all over, in this case, 3. Find a common denominator, so you got 2 pi times, multiply top and bottom by 3, apparently. So you get 24 root 2 all over 15 plus multiply top and bottom by 5. 40 root 2 over 15, which is going to be 2 pi times 64 root 2 over 15, which is, at the end, 128 root 2 over 15 pi's. Okay. All right, what's next? Shifted axis of revolutions now. So non-x-axis, non-y-axis rotations. And the only spiel here is that your radius function will no longer just be x or y. Usually it's something like 4 minus y or something like that. So let's take a look here. This example. This is sort of the region that we've worked with before, so I'm going to dispense with the pleasantries and just plot it. So, what did that region look like? Oh, we want to rotate about x equals 4, vertical line at 4. So, geez. So we have 1, 2, 1, 2, 3, 4. Remember that one graph went like this, and then the other graph went like this. Okay, and this is the region. 2, 3, 4. The line we want to rotate about is this line here. And the rectangles for shells are parallel to the axis of rotation. So if we're rotating about that line, it's kind of parallel to the x-axis. Right. So I need a height function and a radius function. The radius is going to be a little different, right? The rectangle is located at x sub I in this case, and it's oriented such that the Riemann man is going in this direction and collecting those volumes. What volumes is this idiot collecting? It's if I were to rotate out that red rectangle, it'd be pretty huge. You know, it's going to be, this is one of our shells. Okay. And where is the red rectangle now? It's sitting right here. Okay. So my point is, in order to get the radius, what we're looking for is kind of the distance from here to the axis of rotation. Okay, so I need a formula for that distance in order to get my P of x formula. So what is that distance? And it turns out just to be the difference between two distances, right? It's this distance, which is constant, minus this distance, which is just the distance to the rectangle, which is x sub I, right? So it's this long distance, which is 4, minus the actual distance to the rectangle, which is, in this case, x sub I, or just x. And then the height of the rectangle is, again, a difference. In this case, it's the difference between this height. The red rectangle is the difference between this height and this little height, which are given by the parabola 4x minus x squared, and then the lower height is given by x squared. Okay. Okie dokie. So let's go ahead and get our integral set up. So it's 2 pi times p of x, which we're saying is 4 minus x, times h of x, which is the 4x minus x squared would be minus 2x squared dx. And the Riemann man is going from 0 to 2. So 0 to 2, wherever the region is, basically. And then you just have an integral. Okay, so again, it's just 2 pi integral of, have to do some distributions, so 16x minus 8x squared minus 4x squared is minus 12x squared, and then plus 2x cubes dx. And then antiderivative, 16x squared over 2 is 8x squared. 12x cubed over 3 is 4x cubed. 2x to the 4th over 4 is x to the 4th over 2. And evaluate from 0 to 2. So 2 pi times 8 times 4 is 32, sorry. Minus 8 times 4 again is 32, and then plus 16 over 2, which is 8. So it looks like it's just going to be 16 pi's for the volume. Okay, great. Why do we have the shell method at all? It seems like you just always do the disk method, right? So the problem is this issue with where you're ending up with two regions. Okay, so let's go back and reinvest a problem similar to this and kind of do a compare and contrast. Disk versus shell. Okay. So our region is given by y equals 1 over square root of x plus 1 y equals 0, x equals 0, and x equals 4. And I want to do an x-axis rotation. Okay. So get the region. So 0 to 4, 2, 3, 4. At 0, y is 1 over 0 plus 1 square root of, so it's 1 over 1. So it's just 1. And then at 4, it's 1 over square root 5, which is down here somewhere. Okay. So that y equals 0 is the x-axis, x equals 0 is the y-axis. So it's this region we're rotating, and we're going about the x-axis. Okay. So first, kind of the way you kind of don't want to do it is to use the shell. Okay. So why? And it's because of that two-region issue. Okay. So for the shell method, again, for shell, the rectangles are parallel to the axis of rotation. So your rectangle in the first region is right here, and then the second region is variable. So you have to have two different integrals, okay, for these guys. So there are these like your y sub I and your y sub I. Right. So the orientation, the Riemann-Man is going up the flagpole, collecting those volumes. And like I said, you need two integrals. So in the first region, the radius is just y, but the height function is constant. The height function is just 4. Okay? In the second region, the radius function, again, is y, but the height function now is variable. Okay? And we need to go to our formula to get the height function in terms of y. So I need to solve this for y. Maybe go over here and do that. So y equals 1 over square root x plus 1. Square both sides. Y squared is 1 over x plus 1. Multiply both sides by x plus 1. Divide both sides by y squared. You end up with x plus 1 equals 1 over y squared. And then finally, x equals 1 over y squared minus 1. So the second height function is just that, the 1 over y squared minus 1. And what you're ending up with is two integrals. So you'll end up with the first integral from 0 to pi, from 0 to the y value of this point here. So that point is at 4 comma 1 over square root of 4 plus 1, which is 5. So you're going from 0 to, so that's another complicating issue, which would suggest you don't want to use this method. Okay, and on the inside, of course, we have 4y dy, and then plus 2 pi on this other integral. I'm going from 1 over square root 5 to the y coordinate up here, which is, of course, 1. So we have 1 here, and then you have y times 1 over y squared minus 1 dy. Okay, so this doesn't look like a lot of fun to integrate. Not fun. Set face. Okay. So maybe the disk method would be the better method, and it turns out it is. So for the disk method, your rectangles, let's do those then in blue. You only need one integral. Okay, and in this case, the Riemann-Man is running across the x-axis, collecting all of these disks. You need a radius function for this method, and that's pretty much it. It's not a washer. There's no hole in the resulting object, and it's in terms of x. The base of the rectangle is on the x-axis, and the formula is given. It's just 1 all over the square root of x plus 1. So for the disk method, it's always pi r squared. So pi times the integral of 1 all over square root of x plus 1 squared. The Riemann-Man is going from 0 to 4 on the x-axis, dx. And then, I mean, that's it. And the cool thing is when you do this method, then that square root's going to go away. So you just get pi times the integral of 1 over x plus 1 dx. and then that's a natural log, right? So pi ln absolute value x plus 1. If you do a u sub, there's no constants floating about from 0 to 4. If you plug in 4, you get ln 5. If you plug in 0, you get ln 1, which is 0. So you just get pi times ln 5 for your answer. Okay. So yeah, one way is sometimes way harder than the other, and usually the bad choice will snowball on you to the point where you'll say, there's no way I want to do that integral, or I don't even know how to set up that integral, is another thing you may start saying to yourself. Okay, let's look at one of the problems in WebAssign. So there's this torus problem I wanted to look at. Stay signed in, please. Oh, this one's kind of weird down here. This number 9, where you have y equals 6 minus x. The radius function actually needs to be negative because the height function is just going to be, 9 minus 6 minus y. But when you're multiplying things out for volumes and adding up those volumes, the y values will all be negative. So you end up with a negative volume. I mean, if you didn't get it, you would end up with negative 9 pi as your answer. And you just make it positive. But the way you want to do it is kind of handle it like you have to make the radius negative y instead of just y. So that number 9 is kind of a curveball. Hopefully you can think your way through it. Number 8 is the one I want to look at. So we want to rotate a circle region about the line x equals 8. Okay, so let's do that. The math involved with the integral is really where it becomes interesting. So let's take a look. Okay, this is number 8 in WebAssign. And we have a circle, x squared plus y squared minus x squared plus y squared equals 36. So it's a circle with radius 6. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It's going to be an ugly circle. 1, 2, 3, 4, 5, 6. We want to rotate it about the line y x equals 8, 6, 7, 8. So that's this line right here. And we're in the shell method, so let's use a shell to do this. So the rectangles we are rotating will be like this. Shells are parallel, so the Riemann man is going to have to smush them in over here. I put them in white. This person is collecting his shells in that direction, going from -6 to +6. You have to be careful because the shells, you can't kind of use symmetry in this case because the volumes of the shells on the left here are much greater than the volumes inside. If you think about it, you're rotating that region way around like this. The volume of something like this is way bigger than the volume of something like this. Okay, so anyways, as usual, where is this thing located? It's located at position x of I. In here, I need a radius function, I need a height function, and it's a shifted axis. So the radius function is not just going to be x. Okay, so for the radius function, it's a difference, right? It's the difference between this distance to the axis of rotation, and then for this particular red rectangle that we're dealing with, minus the distance to the rectangle from the x-axis. So the distance to the axis of rotation is just 8, and then you're subtracting away the distance to the rectangle, which is located at position x of I, so just 8 minus x. Okay. The height function, h of x, then is going to be given by the height of this rectangle. So the formula for this circle is what? It was x squared plus y squared equals 36. I need a formula in terms of x, so I can solve this for x. In terms of x, solve it for y. In other words, so you get 36 minus x squared, take the square root on both sides, plus minus square root 36 minus x squared. Y equals, the positive is just the top, right? So y equals square root of 36 minus x squared is this blue top curve. So if I use that for my formula, I'm only going to be half correct, right? So if I use square root of 36 minus x squared, it's not going to work. It's only going to give me this distance, okay? In order to get the whole distance, what do you think you do? Well, you're just going to multiply it by 2, okay? And that'll give you the whole distance, or the whole height. Just multiply this by 2. And that's pretty much it. Your integral then will become 2 pi times the integral from -6 to 6 of 8 minus x times 2 times the square root of 36 minus x squared dx. Okay, and now the fun begins, right? So, the first thing you're going to do is probably pull that 2 out, so you end up with I don't know, 4 pi times the integral of 8 minus x times the square root of 36 minus x squared dx. The next thing you're going to do is split it into 2 integrals. You're going to distribute this. Okay, so you're going to have 4 pi times the integral of 8 times the square root of 36 minus x squared minus x times the square root of 36 minus x squared. Okay, so you have a difference inside the integral. You can split that then into 2 integrals, and you end up with 4 pi times 8 times the integral of square root of 36 minus x squared from -6 to 6 dx minus the integral of x times the square root of 36 minus x squared dx from -6 to 6. Okay. The second integral, it may not be obvious, but the inside of the integral is an odd function. And when you're integrating over a symmetric region like that, what you kind of have is a scenario like this, where the regions will cancel each other out. Okay. If you don't like that explanation, you can always do kind of a u sub on here. So you would do a u sub for 36 minus x squared. Du would be -2x dx, and then dx would be -du over 2x. And then if you change the bounds, that's really where you see it. Change the limits. I mean, u of 6 would be 36 minus 36, which is 0. That's what the top limit will change into. So here I am sort of rewriting things, 4 pi 8 integral, not doing anything with the first integral. 36 minus x squared dx minus the second integral, where I just changed the upper limit, and I have what's going to end up being x times the square root of u times -du all over 2x. And then the lower limit is u of -6. So I'm using this formula here, by the way, if you can catch that. U of -6 is also 36 minus -6 squared is 36, so that's also 0. Okay. So you may or may not remember, but when you have an integral going from a to a of whatever, that's just equal to 0 as well. And if you still don't believe me, literally evaluate the integral, and I think you'll find it's going to be 0. Okay, so the x's will cancel out. You pull out the -1/2. Ultimately, though, this thing is just going to be a big 0. Okay. Okay. That first integral then is the troublemaker now, right? So we have 4 pi times 8 times the integral. Let's rewrite that as 32 pi 8 times 4, 32 pi times the integral of -6 to 6 of the square root of 36 minus x squared dx. Okay. You'll see in the homework, they give you a hint that this integral is the area of a semicircle. Okay, this integral right here that we have just written out. The integrand here, is y equals square root of 36 minus x squared. And if you look above, y equals square root of 36 minus x, that's just that blue curve there. That's the upper semicircle, right? So if you draw the picture, the integral from -6 to 6 of square root 36 minus x squared is the area of 1/2 of a circle with radius 6. Okay, so this integral represents this area. Okay, so what is that area? Well, the area of the full circle, the area of the full circle is pi r squared, right? So it's pi times the radius 6 squared, which is 36 pi. So because this is the area of half the circle, you just multiply that value by 1/2, and you get 32 pi times 1/2 times 36 pi. Okay. Yeah. And so we're almost there at our answer. You have 32 times 18, whatever that is, times pi squared. I'll make my calculator really quick. So 32 times 18 is 576 pi squared. And that should be your answer. Okay. Let's see. Yeah, 576 pi squared. Yay. All right. That's the big and the small of it. We'll leave it there, and we'll see you next time. Thanks for watching.